Hello, mathematicians. Today we are going to be looking at the derivatives of logarithmic and exponential functions. Let's get started. So if we have y equals e to the x, this is known as the self-deriving function. The derivative of e to the x is actually just e to the x. Now, if I have y equals e to the power of f of x, where f of x is some other function, then essentially I want to apply the chain rule here. So we would take the derivative of the outside function. So the derivative of e to the x is just itself. And then I want to multiply by the derivative of the inside function. Let's do some examples. Example 1, find the derivative of y equals 2 to the power. Find the derivative of y equals 2 times e to the x plus e to the minus 3x. So in this case, dy dx is going to be equal to 2 times e to the x. So the coefficient in front does not change, it just stays. And then we take the derivative of e to the x, which is e to the x. Then we want to add that with e to the minus 3x and multiply that with the derivative of minus 3x, which is minus 3. So here's our final answer. Pause this video now and try example 2. All right, let's check our answers. dy dx will be equal to e to the 3x squared plus 2 times 6x. And that's it. So now let's apply this with some derivative rules. We can try this both using the quotient rule and then also the product rule and seeing if our answers are equal. We'll start with the quotient rule. So for the quotient rule, we take the denominator value, multiply by the derivative of the numerator, then subtract the numerator times the derivative of the denominator, and then we want to divide by the denominator squared. In other words, low d high minus high d low, square the bottom, and away we go. That's the mnemonic device that we used. And we might be able to simplify it a little bit. So we can see that in the numerator, I can factor out an e to the x. And in the denominator, I still have my e to the 2x. We can cancel out some common factors, which leaves us with 1 minus x over e to the x. Let's try this question again, this time using the product rule. In order to do that, we want to rewrite our question as x times e to the minus x. Using the product rule, we can first take the left function and multiply by the derivative of the right function, and then add that with the derivative of the left function, which is x, and multiply that with the right function. So let's rewrite that. All right, so right now, these two answers that we have don't look like each other at all. So let's rewrite what we have here on the right-hand side and see if we can make it look like the answer that we got on the left-hand side with the quotient rule. So applying my exponent properties, e to the negative x is just 1 over e to the x. Now I have common denominators between both my terms, and the numerator can be rewritten as 1 minus x, and my common denominator is e to the x. So now we have both sides are equivalent. I have solved both using the quotient rule and the product rule. Here's our next derivative rule. So this one has to do with the natural log function. So if I have y equals ln x, the derivative of that turns out to be 1 over x. If I have y equals ln of f of x, in other words, there's another function within my log function, then again, I want to apply the chain rule. So first I take the derivative of my outside function, which is going to be 1 over f of x. And then I want to multiply by the derivative of my inside function. Question 4. Find the gradient function of y equals ln of 3x minus 2. So remember that if I have y equals ln of f of x, the derivative of that is just going to be f prime of x over f of x. So dy dx, in this case, is going to be equal to 3 over 3x minus 2. And we're done. Pause the video now, actually pause it, and try the next 2 questions. Okay, let's look at the answers together. So for example 5, dy dx is going to be equal to 2x plus 1 over x. For example 6, dy dx is equal to, so we are going to have to apply the product rule here. So let's first take the derivative of this left function, multiply by the right function, and then we want to add that with left function times the derivative of the right function. We can simplify this a little bit to get 2 ln x plus x. And we're done. So in some scenarios, if we are given a log function to derive, use log properties because sometimes that can make it easier for us to find the derivative. So we're going to attempt this question twice, once using the product rule in combination with the chain rule, and then we're going to use it again, but this time we'll apply our log properties first. So let's try using the product rule plus the chain rule. If I were to look for dy dx of ln of x times e to the minus x, I first take the derivative of the outside function, which gives me 1 over x times e to the minus x. Then I have to take the derivative of that inside function. So here's my inside function, x times e to the minus x. I need to apply the product rule here. So that's going to get me x times negative e to the minus x plus 1 times e to the minus x. Let's try to simplify this a little bit. So I'm going to get, let's factor out an e to the minus x in the numerator, leaving us with x, let's see, minus x plus 1. And that is all divided by x times e to the minus x. And if I rewrite that again, I'll have 1 minus x over x. Let's try with log properties this time. So remember that I have a log property which states if I have an argument where I have 2 terms being multiplied, then I can break that logarithm apart by addition. So we can rewrite the function y as ln of x plus ln of e to the minus x. But notice that this simplifies even further. So I can apply another log property, not on the first term, but on the second term, which allows me to bring that exponent value in front as a coefficient. So that becomes minus x times ln of e. And in fact, that simplifies even more because ln of e is just 1. So when I rewrite my y function, I'm going to be left with ln of x minus x. So now if I take the derivative of that function, I have a much easier job. The derivative of ln x is 1 over x, and the derivative of minus x is just minus 1. It doesn't quite look like the function that I have on the left-hand side, but if I rewrite this a little bit, so for example, if I rewrite the function on the left here, I can write it as 1 over x minus 1, just by taking each term in the numerator and dividing by x, and I can see both are equivalent. please take some time to practice these 5 questions on your own. You're welcome to use the whiteboard space in the classroom as you do so. When we come back, we're going to look at the last 2 examples together. All right, it is time to revisit some familiar problems, but this time with new functions. Example 8. Find the value of x where the function y equals x times e to the minus x has a horizontal tangent. So again, let's first find the derivative by applying the product rule. So the derivative of x times e to the minus x is going to be x times minus e to the minus x plus 1 times e to the minus x. That gives us minus x e to the minus x plus e to the minus x. This is going to have a horizontal tangent when the derivative is equal to 0. And that's because the gradient of a horizontal line is 0. So actually, let's rewrite that derivative function so it looks a bit nicer. Okay, I'm going to combine this into a single fraction, giving me 1 minus x over e to the x. So there we go. There's the equation I'm asked to solve. Multiply both sides by e to the x, and I'm left with 0 is equal to 1 minus x, and x is equal to 1. So at 1, my function y equals x times e to the minus x has a horizontal tangent line. Final question. Find the gradient of the function y equals ln of x squared plus 4 at the point 1, ln 5. So we'll start by looking for the gradient function. So to do that, I want 1 over x squared plus 4, and then I want to multiply that with the derivative of the inside function, which is 2x. Okay, so there's my gradient function. And I want to know exactly what that slope value is at the point 1, ln 5. So we're going to plug in x equal 1 into my derivative. That gives me 2 times 1 over 1 squared plus 4, which is 2 over 5. And we are done. Now, you might be asked an extension question here, and a natural extension to this would be find the equation of the tangent and normal. So this value, 2 over 5, already gives us the slope of the tangent line. We have a point, xy, that is on the line. So we can apply the point slope formula here to find the equation of our tangent line. You might also be asked to find the equation of the normal line, remembering that the slope of the normal line will have a negative reciprocal slope to the slope of the tangent line. So our normal line will have a slope of minus 5 over 2, and it will also cross this point 1, ln 5. So you can give those a try and see if you can refresh your memory of tangents and normals as they relate to these new derivative functions. That's it for today. We have some cognitive homework that will be released in the last 20 minutes of class. See you next class.